This is our second trigonometric substitution video. In this video I'm going to do an example for you. It turns out we've got to do a u-sub first, and then it turns out to be a tangent substitution after we've done the u-sub. Notice you've got this integral with an x squared minus 2x plus 2 all raised to the 3/2 power. That x squared minus 2x, or that form x squared plus bx, makes me think of completing the square from that first section that we discussed. So first I'd ask myself, that's where I'm going. But first we should always go through our list. Do I have a basic rule for that? Absolutely not. I don't have any basic rules for polynomials in the denominator raised to rational powers. It's not in there. Can I do a u-sub? Can I just do a straight u-sub and get to avoid completing the square? Turns out I can't. If I were to do u-sub, u would have to be this entire inside function. The derivative of x squared minus 2x plus 2 is 2x minus 2, and then I have all of that times dx. I don't have a 2x minus 2 up here, and I can't multiply it by something to get a 1 that doesn't involve x. It's not going to be a u-sub, not in its current form. But I noticed the x squared plus bx, and from our first section I know that whenever I have an x squared plus bx, by completing the square is a good option. So I'm going to complete the square, and I'm completing the square on this function that's inside. So I'm going to start with that. Now don't forget, if there is a number in front of that x squared other than a 1, you need to factor that out from the first two terms at least. Since there's already a 1 here, I don't have as much work to do. So I'm just going to leave some space beyond the 2x to complete the square. And I'm going to leave that plus 2 over there. So once you've got a 1 in front of your x squared, the number in front of the x is called b. Take half of that and square it. That's what you're going to add to complete the square. Now remember, if you're adding something here, you can't just add a 1. I mean, you just made it a totally different function. That's not legal. This is no longer equal to this with that 1 there. But if I compensate, if I add the 1 and I also subtract the 1, then I'm good to go. All I've done is add 0. Now this is completely equivalent to this, it's just written in a slightly different form. It's got some extra 1s everywhere. But the idea is, now that it's written this way, I can complete the square. This is a perfect square plus a constant. So we've added and subtracted the 1 to compensate, and now this is a perfect square, so we'll factor it. Two numbers that multiply to give me 1 that add to -2 are -1 and -1. And then you want to simplify that 2 minus 1, it's just a 1. So I'm replacing this, everything that's in those brackets, with the quantity x minus 1 quantity squared plus 1. So this is the same as this. So I'm making a literal replacement. And then of course I always ask myself, all right, if I do that, do I have a rule for that? Do I? You might say, not yet. But notice there's a u squared plus a squared right there. U squared plus a squared kind of looks like an arctan. Now if there was no 3/2 there, it would be an arctan. It would be a u-sub and then an arctan. But there's a 3/2. So we're going to do the u-sub, and then after the u-sub it's going to be a tangent trigonometric substitution. So first let's do our u-sub. U is that inside function, x minus 1. Derivative of x minus 1 is just 1, so we get 1 dx. So our integral can be written entirely in terms of u this way. The square is still there, the plus 1 is still there, the 3/2 is still there. Oops, the dx shouldn't be there. Didn't replace that. All of that is still there, but that x minus 1 is replaced by a u, and the dx turns out to be du. It's exactly the same thing. So this is equal to this. And now I see the u squared plus a squared, and that makes me think of a tangent, that arctangent function. But it's not an arctan because of the 3/2. If it looks like an arctan, but it's not an arctan, and it's not a u-substitution, not in this form anyway, it was a u-sub to get here, then I'm going to do a trig substitution. So I identify a squared. So u squared plus a squared implies we want to let u equal a tan theta, and we're going to do the trig sub from here. So we need to find a, and find u and du and all that jazz. So this is our prepare to substitute step. You want to write everything here in terms of theta. First we have to identify a. A is the constant, or a squared is the constant. A squared is 1, so a is the square root of 1, which is 1. That means that u is 1 times tangent of theta. Du, it's the derivative of tan theta. That's secant squared theta. Don't forget your d theta. And then u squared plus 1. We could write that as the square root of u squared plus 1 quantity cubed. Like, you could write that a lot of different ways that would include a square root. You don't have to. The idea is just to simplify this using our trig identities. So we're going to simplify u squared plus 1. U is tangent. So it's tangent squared plus 1. You recognize it? We did a lot of trig integrals in the last section. I hope you recognize it. Secant squared. So this is replaced by secant squared. Du is replaced by secant squared theta d theta. So now we're going to substitute. So we've prepared to substitute. We calculated u, we calculated du, we calculated u squared plus 1. All right, and now we're going to substitute. We're substituting into this. So I've got the integral of 1 over something to the 3/2. U squared plus 1 turned out to be secant squared. And du was secant squared theta d theta. Please don't forget to do the du. So many students leave that off, and maybe the integral is harder to solve. Maybe it can't be done. But now we're going to simplify. Now, in order to simplify this, we have to remember a little bit of algebra. Keep coming back to these exponent properties. They come up again and again. Remember, if you've got x to a power raised to a power, you want to multiply those exponents. So secant squared to the 3/2 is secant to the 2 times 3/2, or secant cubed. The 2 and that 2 are going to reduce. So we end up with a secant cubed in the denominator and a secant squared in the numerator. And 2 of those secants are going to reduce. You just have a 1 secant in the denominator, but 1 over secant is, remember your reciprocal identities, that's cosine. Oh, so easy, so nice. Now remember, some of them aren't so nice. You might have to do the trigonometric integrals. You might have to use your trigonometric integrals guidelines from the previous section. Now we just anti-differentiate that. Sine of theta plus c. Alright, so we prepared to substitute. And then we substituted. And you simplify so that you can anti-differentiate. The question is, are we done yet? No, absolutely we're not done yet. That is an answer in terms of theta, and I originally started with not even a function of u, I started with this function of x all the way back here. So remember, theta is just something we made up. Theta was something that we made up so that we could evaluate this. And u was something that we made up so that we could evaluate this. And we completed this square so that we could evaluate this. So you got to go all the way back. Originally, this is what this problem was all about. We did all of this to get here. So we're here now. And I'm not done until I've got a function of x that I can differentiate and check against that answer at the very beginning. So the question becomes, how do I get back to x? We prepared to substitute. We substitute. You might remember from the last video, we make a triangle. Seems a little odd to people, but we're making a triangle. It's a triangle whose sides are labeled in terms of x. And we're labeling those sides using the original substitution. And then we're going to use the triangle to find sine of theta plus c, our final answer in terms of x. Or actually, I think we did this trig substitution in terms of u. So I'm going to label the sides not in terms of x, but in terms of u this time. First, we're going to solve that, and then we're going to back substitute to solve the original. All right. So I've got a triangle. I always draw it the same way, with the theta down there. Our original substitution was u equals tan theta. That was the original for the trig sub part anyway. And we would normally get tan theta by itself, but it's already by itself. And so I want to write this as a fraction. So I'm going to write this as u over 1, and then I think back to, oops, I spelled it wrong. Think back to trig, or maybe high school pre-calculus. Remember that? Ah yes, SOHCAHTOA. That's right. Tangent is opposite over adjacent. All of our trig functions are defined in terms of ratios of these right triangles, at least initially. So the side opposite theta is u, when the side adjacent to theta, remember that's next to theta, adjacent and next to are the same thing, but it's not the hypotenuse. The hypotenuse is the other one. So the side adjacent to theta is 1, and this squared plus this squared equals that squared. So 1 squared plus u squared equals the hypotenuse squared. So the hypotenuse equals the square root of u squared plus 1. And you might say, hey, there was a u squared plus 1 in my original trig sub integral. Turns out that that's always the case. That third side is always going to look like that trig substitution, or that expression from the original integral that we started with. That's why this all works out so nicely. Okay, so we're here. And I've got the hypotenuse, I've got the opposite side, I've got the adjacent side. The question was, why was I doing this again? Oh yeah, that's right. We drew the triangle for the purpose of getting these sides labeled in terms of u, and we did that for the purpose of getting this final answer in terms of u. And then eventually we'll get back to x. So I need sine of theta in terms of u. I have sine of theta, according to SOHCAHTOA, that's opposite over hypotenuse. Side opposite theta is a u. The hypotenuse is the square root of u squared plus 1. And then the final thing to do is write your final answer in terms of u. Back substitute. Are we finished yet? Most of the time we would be, but remember, our original problem wasn't about you. Sounds like I'm telling you think too much of yourself. No, it's not about you. It's about me. No, just kidding. It's not about you. It's about x, okay? So we need to get back to x. So we back substitute once to get to u, and then we're going to have to back substitute one more time to get back to x. And remember, u is x minus 1, so we're just going to substitute that in. I'm just going to write down what we've found. We found that the original integral, which was this, is equal to u over the square root. And we said, well, what was u? U was x minus 1. Remember, u is something that we made up so that we could solve this problem. And we could stop there. Or if you want to look in the back of the book, they might say, I don't like that x minus 1 squared. They might write that twice in FOIL. Textbook authors are funny. They're people, just like us. It's hard to know what they want. First times first is x squared, outer times outer is negative x, inner times inner is the same. Last times last is plus 1. 1 plus 1 is a 2. So that's an alternate form of the answer. If you ever start asking yourself, what on earth did I just do? What was the point of that? Remember this. We just took the antiderivative. Antiderivatives are functions. You take the derivative of this guy, after simplification, you're going to get this guy. That's what this is. And trigonometric substitution is just a particular way that we go about finding an antiderivative like this. So we tried basic rules, they didn't work. We tried u-substitution, it didn't work. We tried the 9 techniques, it didn't work. It wasn't an integration by parts problem. It wasn't a trigonometric integral. But with a little bit of a substitution, it looked like an arctan. It wasn't an arctan, so we did a tangent trig substitution, and that got us here. But again, what was the point? What did we do? We found a function. When we take the derivative of that, we should get that. So you can stop here if you want. I'm going to check my answer. I just want to see. Is the derivative of this equal to this? If it's not, I'm going to have to scrap this video and start again because I did something wrong. I don't think we did anything wrong. Just in case though. There's always that option. Buy yourself a big eraser, doing some math. What it takes, it's okay. Alright, so I've got the derivative with respect to x of this. Derivative of the sum is the sum of the derivatives. Take the derivative of the first and add the derivative of the second. Derivative of the constant is 0. How do we take the derivative of this? You guys remember? It's the quotient rule. Derivative of f over g is g times f prime minus f times g prime over g squared. Now I said it that way because that's a very nice professional way to say it. But that's not really what I was thinking. What I was thinking is this is my high function and this is my low function. And Mr. Pink, my high school calculus teacher, drilled this into my brain and I will never forget it. The derivative of high over low is low d high. This is what I say to myself in my head. Low d high minus high d low over low low. And the d is an operator. It applies to whatever's in front of it. So it's the bottom function, low d high, minus high d low, top function, times the derivative of the bottom function, all over the bottom function squared. Great mnemonic, very easy to remember. Low d high minus high d low over low low. That's exactly what I'm going to do right here. We're going to have to do a little chain rule whenever we take the derivative of the denominator as well. Okay, so we're thinking about this. Thank you, Mr. Pink. And I get low D high. I'm just going to write it down. I'm not going to do it yet. Minus high. Don't forget those parentheses. You got more than one term. You need parentheses. Otherwise, the negative is only going to apply to the x and then be wrong. We went minus high. D low. A lot of work to do there. Didn't quite leave myself enough space. I'm just going to write it very small. All over. Low, low. Got that. Bam, I'm going to square it. All right, so we're here. Derivative of x minus 1, that's just 1, no problem. And this piece, a little bit more challenging. This requires the chain rule. You've got all of this raised to the 1/2 power. So we've got an inside function. Remember, the chain rule tells us take the derivative of the outside first. Derivative of a function to the 1/2 is 1/2 of that function to the negative 1/2. Put the inside function back in, don't do anything with it yet. And then don't forget to multiply by the derivative of the inside by the chain rule. Derivative of this guy is 2x minus 2. All of that gets divided by all of this. If you square something and then you take this, or you take the square root and then you square it, it's going to get rid of that. As long as it's positive, but okay, we're not going to worry about those details right now. All right, so we've got x squared minus 2x plus 2. Actually, it turns out that it's always positive because it's x minus 1 squared plus 1. So we're good. Anyway, sorry about the aside. This is my answer. You might say, Miss Townsend, that does not look anything like that, and you'd be absolutely right. My hope is that with a little bit of algebra, though, it will. So let's see what we can do. All right, so I've got x squared minus 2x plus 2 all to the 1/2. And then over here I've got this times this times this times this. All right. Well, the 1/2 times this, if I distribute, 1/2 times 2x minus 2 is 1/2 times 2x, which is x. And 1/2 times negative 2 is negative 1. So this times this is x minus 1, and there's already an x minus 1, so I've got two of them. Not two of them, but x minus 1 times x minus 1, so two of them. And then I'm taking care of that, and that, and that. And that is square root of x squared minus 2x plus 2. Or if you prefer, just write it as x squared minus 2x plus 2 all to the 1/2 in the denominator. But it's still, we're still also dividing by x squared minus 2x plus 2. To the first, keep that in mind. Still not looking like the way, not looking the way I want it to look yet. Does not look like my original integrand. But we have complex fractions. I mean, I can't expect this to look like that. It's obviously too complicated. No, it's too complicated right now. But I need to get rid of this. I need to get rid of this guy somehow. That's easy. If I want to get rid of this fraction, I want to get rid of this denominator, I just need to multiply this whole level, this whole numerator by this denominator, and then it'll be gone. That's legal, as long as I also do the same thing down there. Anything I do to the numerator, I have to do to the denominator, because then I'm not changing anything. Then I'm just multiplying by 1. Multiplying by 1 is totally fine. So we're going to distribute. We're going to have that times that minus that times that. And you've got this times this. So I've got this to the 1/2 times that to the 1/2, it's the same thing. That to the 1/2 times that to the 1/2 is that to the first. So I don't even need parentheses anymore. So I get that guy. And when I multiply this by this, I just have a minus the quantity x minus 1 squared. Down here, I've got this to the first times the exact same thing to the 1/2. Remember that old exponent property? What am I going to tell you to do? I'm going to tell you to add the exponents. I always do. Add those exponents. Bam. All right, still doesn't look like my integrand, but it could. If I expand this and distribute the negative, our hope is this beautiful numerator is a 1. It may be a 1. It may not be. We may have made a mistake, but we will not know until we check. So we're going to do a little bit more work. All right, I've got this. X minus 1 squared is x minus 1 times x minus 1. You might say, Miss Townsend, I already know what x minus 1 squared is. Good for you. Not everybody does. That's why we show our work. We're all at different levels. That's totally okay. Gotta start somewhere. And it never hurts us to review a little algebra. Not for most people, not in Calc 2. Okay, so if I FOIL this, first times first is x squared. Outer times outer is negative x. Inner times inner is another negative x. Last times last is a positive 1. Distribute that negative, and we get this minus this. Distribute the negative. Negative and a negative is positive. Negative. There's negative 1. Do I get a 1 in my numerator? You see it? It's gone. It's gone. What's 2 minus 1? It's 1! That's right, guys. Sorry, I'm being really cheesy in this particular video. I'm getting too comfortable with you guys. The audience that does not yet exist. It's for my students for next semester. You probably already exist, but you know what I mean. You're not watching it yet. There we go. That's our original integrand. Yay. All right. So, the derivative of the antiderivative gave me the function back. Always a good thing. It means you did it right. So, this truly is the antiderivative of this. And how did we do it? What was the point of this video? It's been 20 minutes since we finished antidifferentiating. No, it isn't. I actually don't know. What did we do? We completed this square. Once we completed this square, we did a u-sub, and then we said, hey, that looks like an arctan, but it's not quite an arctan. So let's do a tangent substitution. And then we did our 4 steps. Just prepare to substitute. Figure out what a is, find u, find du, find u squared plus 1, get all that ready, and then sub it in. And then simplify. And then when you get down here, anti-differentiate. And then trying to get that in terms of u, so you can get it in terms of x. How do we get this in terms of u? Draw our triangle. We'll label the sides. You label the sides using the original substitution. Then you say, okay, what do I need? I need a sign. Not an SIGN sign, not praying, I need a sign. No, I need a sine, S-I-G, or S-I-N-E of theta. So I look at my triangle. I know I need sine, which is opposite over hypotenuse. I find the opposite. I find the hypotenuse. I plug them in. That goes there. And then don't forget to back substitute. We back substituted sine of theta for this, and then we got to back substitute one more time. U is the same as x minus 1. And if I want to go even further, simplify that so it looks like the answer in the back of the book is going to look like that. probably. Take derivatives, check. And after a whole lot of Calc 1 review, which many of us need, and a little bit of algebra review, we got here and we know we did it right. Thanks for your attention, guys. Sorry that video got a little silly.